I did it.
Can you guys see my PowerPoint?
Okay, we are starting officially. This is being recorded. Thank you for the UrbanARK team. I guess I'll see what's going on my phone. So let's begin, and thank you all.
Terry, can you guys actually see this?
Yep, I can see it.
Hold on. I think I've pulled up the wrong thing. Sorry. Give me just a second. I pulled up Aaron's instead. There we go. There. So good morning, everybody. For those of you who don't know me, I'm Deborah Lafer. I'm the US-based principal investigator on this NSF grant, National Science Foundation grant, that we're going to tell you a little bit about. Oops, oops, sorry. You would think after a year I would have this completely under control, but clearly not. There we go. So, let's see. Okay, so hopefully you can now see this in full screen mode. The project is called UrbanARK, and it's about the assessment and risk management of coastal areas for flooding. But as Terry mentioned, we're going to just show you a little piece of the work today. To give you an idea, this is a US-Ireland program. It involves researchers in the United States here at NYU, in the Republic of Ireland at the University College Dublin, and in Northern Ireland up at Queen's University Belfast. And it gives you a little bit of a breakdown of kind of the areas that each of the universities are kind of, I wouldn't say contributing, but leading from the data collection all the way to the enhanced hydrological model. So today we're just going to be talking about some aerial Lidar, some subsurface identification, and some alternative terrestrial remote sensing. Our current team is made up of these three universities, myself and Raul Lejano here at NYU, supported by our postdoc Evan O'Keefe. The University College Dublin team is led by Michaela Bertolotto, and that's her team with Anne Lecoq, our senior research fellow Anne Vouveau, who you'll be hearing from today, our PhD candidate Shamin Hawaj, and then over on the Belfast side, we're going to, our PIs, Ulrich Offendinger, with co-PIs David Hughes, Jennifer McKinley, and John Manili. That presentation is going to be led today by doctoral candidate Aaron Miller, but most of these people are on the line today and can, really provide any answers to questions you might have. So I'm very pleased to see so many people from DEP, from DDC, as well as some of our Irish municipal colleagues. So thank you so much for coming today. And I think with that, we will turn the presentation over to Vu.
Yep, thank you. Let me try to share my screen first. I hope you can see my screen now.
Perfect.
So good morning and good afternoon, everyone. My name is Anvo Võ, and I'm an UrbanARK researcher based in University College Dublin. It is my pleasure to have the opportunity to present our research to you today. So as you may already know, the UrbanARK team is developing two algorithmic approaches for detection of urban subsurface structures using aerial LiDAR data. So I'm presenting today on behalf of the UrbanARK team in UCD and Professor Michaela Bertolotto, the UCD principal investigator, and other colleagues are also in the audience. They will be joining in the discussion and Q&A. So that is the outline of the presentation. I will first provide an overview of LiDAR technology and LiDAR data, and then I will go on to introduce the two approaches. We call them the geometric approach and the radiometric approach. So LiDAR is an acronym for light detection and ranging. Essentially, it's a technology that uses light, usually in the form of a laser, to measure range or distance. The diagram you see on the screen shows the operating principle of the most common type of LiDAR, which is called time-of-flight LiDAR. Here we have a LiDAR sensor on the left-hand side, and on the right-hand side, we have a target surface. What we aim to achieve here is to measure the range value R, which is the distance between the sensor and the target object. To do that, the sensor emits a laser pulse, which is a strong and short impulse of optical energy towards the target surface. The sensor then captures the time for the laser pulse to travel to the target surface and back to the sensor. That amount of time is denoted as t, parameter t here in the equation. And when we know the travel time and the traveling velocity, yes, we know how fast light travels. Then we can calculate the traveling distance. Because it is a round trip, so we need to divide the traveling distance by 2 to obtain the range value. So that's basically the principle behind the most LiDAR systems. There are 2 additional points I want to highlight here. First, LiDAR is an active sensing technology, meaning that it illuminates the target objects by its own radiation. So LiDAR can see in the dark. It can see objects that do not consistently receive sunlight, such as basements. But it is important to keep in mind that LiDAR relies on the line of sight. There must not be any obstruction between the sensor and the target objects to be captured. Second, in addition to measuring distance, most LiDAR sensors record the strength of the reflected laser signal. So in the presentation, I use the term LiDAR intensity to refer to that signal strength. And that intensity value represents the radiometric property of the target objects. You can think of it like how reflective the target object is to LiDAR. So if you have heard about LiDAR before, there's a good chance that you know LiDAR as a 3D mapping technology. But what I introduce here is a ranging technology. So what's happening here is that this LiDAR sensor is very often used in conjunction with additional sensors for 3D mapping. The LiDAR itself can do ranging only, but we can incorporate the LiDAR sensor with additional mechanisms to do 3D mapping. So, for example, in the animation you are seeing here, a LiDAR sensor is mounted on a helicopter. A scanning mechanism sweeps the laser across the flytrack, and together with the movement of the helicopter, let me play the animation again. So together with the movement of the helicopter, we can cover not only a single point, but a large spatial extent along the flytrack. And by combining the raw ranging data from the LiDAR with the angle of the laser beam, as well as the position and orientation of the helicopter, we can derive a 3D representation of the scene we fly over. So that is an overview. That is an example of such a 3D representation captured by airborne LiDAR. Let me show you in an interactive form. So that is the 3D representation that captured by LiDAR. The area you are seeing here is 370 J Street. That is Center for Urban Science and Progress. That is One Metro Tech and Divisional Library of NYU Tandon. Let me switch back to the presentation. So the data captured by LiDAR are usually referred to as 3D point clouds. A point cloud is a spatially coherent but unorganized set of 3D points. If you open a LiDAR data file and look at the number inside, you will see that a point cloud is composed of a set of point records. Each record or each row in the table represents a spatial point, and a record contains the 3D coordinates of the point as well as additional attributes such as intensity values. Lidar is being collected at the national scale in the US. The US Geological Survey is working on a decade-long project, which is called 3D Elevation Program, to map the entire United States in 3D using Lidar. As of March last year, more than 60% of the country had been covered. And the dark green areas on the map you see on the screen indicate areas where 3D data are available or currently being collected. The project is expected to complete by 2023, and one of the main use of Lidar is to create digital elevation models, including digital terrain models, digital surface models. The USGS has identified more than 600 business use cases potentially benefited from Lidar and data products derived from Lidar. The top one on the list is flood risk management. One of the biggest contributors to the project is FEMA, the Federal Emergency Management Agency. Why this information is relevant to us? First, Lidar data are widely available, and there will be greater availability in the near future. So it is important to invest now in developing tools that allow us to turn the raw data into actionable information. And second, the amount of data collected in such gigantic project is massive. As of 2019, 3D Elevation Program had made available 12 trillion data points in a public repository, and that was less than half of the total project size. Such an amount of data could very easily defeat many traditional computational solutions, and that calls for more powerful, more efficient computing approaches. And that is exactly what motivates our research here at UCD. We are working hard on developing innovative Lidar data management and analysis algorithms that can take advantage of massively parallel computing infrastructure to tackle the large and increasing volumes of Lidar data. And the algorithms for subsurface structure detection are part of the research outcome emerged along the research direction. So before discussing the geometric approach, let me go straight in and share with you an example of the result that we obtained from the algorithm. The video is loading. Yeah, so you are seeing a three-dimensional point cloud colored in gray, and the green points overlaying the point cloud are the subterranean points that were automatically extracted. Here you can see an outdoor staircase that leads from the ground level to a basement at the back of a tall building in Dublin city centre. I'm continuing the video. So if you know Dublin, you may know the Science Gallery, which is part of Trinity College Dublin campus. And across the road from the building, we have some Georgian terrace houses. As typical in Georgian architecture, the houses have front basements visible from the street, and the back gardens are lower than the surrounding terrain. The cross-section showing up in a couple of seconds may show you the structures clearer. So this is the cross-section we are waiting for. Again, the green points are those detected as reflections received from subterranean structures. As you can see, the front basement and back gardens were successfully detected and extracted by the algorithm I'm presenting today. So the reason we in UrbanARK are interested in developing such an algorithm is because subterranean structures have an important role in flood risk assessment. First, the structures laying below the ground level, particularly those used for residential purposes, are more vulnerable to flooding, and we need the knowledge of such structures to better analyze the risk and the vulnerability. Second, we see that subterranean structures are important for accurately predicting flooding. Those structures have impacts on the dynamics of the flood flow as well as the inundation level in a flood event. But most existing flood models do not account for the impacts of subterranean structures. Our geometric algorithm has four main characteristics. First, it is based on a very simple geometric principle. Second, it is parallel. More precisely, it is massively parallel. And massively parallel is not a marketing term. It's actually a technical one. The term refers to the use of a very large number of computer processors, potentially from multiple computers, to massively reduce the computational time. So the reduction can be in the range of several hundreds of times. And that characteristic is related to the third one, which is scalable. Because of the ability to compute in parallel, the algorithm is suitable for dealing with a large amount of data and to cope with future increases in data volume. And that's the key characteristic that distinguishes our work from others. The last characteristic is robust. We have tested the algorithm under various scenarios using different kinds of data in all of our 3 study sites in Dublin, Brooklyn, and Belfast. And we see that the algorithm works consistently. So here is the simple principle behind the algorithm. The data to be analyzed is a 3D point cloud that contains geometric samples from the terrain as well as above ground and below ground objects. We assume that we have a digital terrain model that gives us ground elevation over the area of interest. Those are shown in red color. And you can think of a DTM as a membrane that cuts through the point cloud and separates above terrain and below terrain data points. What we need to do in order to use the DTM to detect or extract subterranean points from the point cloud is to line up each point in the point cloud with its corresponding ground elevation indicated by the DTM. The point cloud is irregularly distributed, as you see in the figure on the left-hand side. And unlike the point cloud, the DTM is often represented as a raster, meaning that the elevation values are structures in a regular spatial grid consisting of cells or pixels arranged in columns and rows, as you see in the figure on the right-hand side. So you may remember from the earlier introduction of LiDAR data that the geometric component of a LiDAR point is represented as a triplet of X and Y and Z coordinates, usually in a geographic coordinate system. And each raster cell in the DTM is represented by its raster index and an elevation value Z. The raster index is a second-order tuple that contains the row index and the column index of the cell, which are identified in the discrete coordinate system of the raster. So our job is to transform the two input data sets in an agreed format and an agreed coordinate system so that they can be linked together. The format that we selected is the raster format of the DTM. In other words, what we do is to rasterize the point cloud. And after the rasterization, we have a common index, which is the second order tuple here for both the point cloud and the DTM. And at this stage, the trend is very straightforward, except that both of the input datasets are very large. Each can contain several billions of records, and training such large datasets is computationally complex and time-consuming. The algorithm that we developed has an efficient way to team up multiple processors from many machines to perform the complex and demanding operation very rapidly. Just to give you a quick sense, we tested a relatively large dataset of 1.4 billion points here in Dublin, and performing the detection took almost 2 hours with one single core. But by connecting 128 cores together, we were able to reduce the processing time to just over 2 minutes. And that computational efficiency behind the parallel trend is actually the main accomplishment from the research point of view. But as it is not the focus of our discussion today, I will not go further to provide details of how we actually did it. Instead, I'm sharing a few more examples of the results that we obtained, this time for an area in Brooklyn, so that I hope you can get a clearer idea of what the algorithm is capable of. And this is the input point cloud on the left and the digital terrain model on the right that we used. The point cloud shown on the left is part of an aerial LiDAR survey Professor Deborah Lafer undertook in 2019 over the Sunset Park area in Brooklyn. The point density of this dataset is over 500 points per square meter, which is 50 times higher than the typical aerial LiDAR point density. That high density is very critical to the success of the algorithm. And the DTM shown on the right-hand side is part of the New York City topopathymetric LiDAR dataset collected in 2017. The resolution of that dataset is 1 foot. And this is the output of the algorithm. From this angle, you may only see that we have quite a few segments of points detected and colored in green. But we need to look closer to see what they are. This is the first point segment. It is a staircase in front of a brownstone house, very typical in Brooklyn. The staircase is very difficult to see from the Google Street View image on the right, but it's crystal clear in the point cloud and was successfully picked up by our algorithm. And this is another example. This time, a staircase at the back of a building. Again, from the Google Earth image, it's difficult to say that the building has a basement, but the LiDAR data gave us that information. This is actually a quite interesting example from the air. We can see stuff in the backyards, and that view is not usually available in other technologies like Google Street View or mobile laser scanning. The last example I want to share is not from a house, but from some kind of urban infrastructure, which looks like a ventilation shaft of the subway system. The structure sits on a traffic island. The structure has a part that is lower than the street level, and that has a covering grades, which are not entirely solid. What we see here is that the LiDAR beams were able to penetrate through that cover and capture the lower points underneath, and our algorithm was able to detect those as well. Now I'm moving on to the second approach called the radiometric approach. There is actually some initial thoughts that we had when we heard about the sidewalk vault problem in New York. The geometric approach I just presented would not be able to detect those that are covered unless the covers are open, like the image on the left-hand side. But in addition to the geometric information, LiDAR also captures the radiometric properties of the scanned object. And that geometric information represented on the last column, column I, or intensity, in our table here. To recap what we mentioned before, the intensity attribute indicates the strength of the laser signal when it is received at the sensor. That attribute partially represents the reflectivity of the target surface. In other words, the radiometric properties of the surface. And our hypothesis is that the radiometric data can be used to detect the covers of some sidewalk vaults if the covers are made of materials that are distinguishable from surrounding pavement. And that is an initial result that we have. Looking at the Google Street View image on the right, you see that between the two subway entrances, we have, looking at the area between the subway entrances, there's a metal plate covering the access point to a sidewalk vault. And in the LiDAR image on the left-hand side, that plate is shown up as a small segment of points in blue colors. In this image, blue indicates low intensity or low reflectivity surfaces, and red indicates high intensity or high reflectivity surfaces. We have not normalized the intensity values here to eliminate unwanted effects of range and the angle of incidence. So the result that you are seeing is not the best possible one. Also, using the radiometric approach is not as simple as selecting points that have intensity values that fall within a certain range. A better way to use that is to combine the radiometric attribute with geometric information. For example, we can perform a spatial clustering operation to group nearby points that have similar intensity values. Then we could potentially extract the shape, the size, and the location of each cluster. And those derived information then become the input to the object detection process. Nevertheless, the covering plate in this example is quite small, and even with the high density airborne data, detecting such small objects is quite challenging. Airborne LiDAR data is fast and is suitable for large-scale mapping projects. It is also good at capturing structures that are not visible from normal public views like the backyards you saw before. But airborne LiDAR is limited in terms of data density and accuracy when we compare it with other technologies that capture data from the street level. And with that, I would want to conclude my part of the presentation here and turn it over to my colleague Aaron Miller from Queen's University Belfast for his presentation on one of the alternative ground-based LiDAR technologies. Yep, let me stop my sharing.
Thanks, Let me see if I can get it here. Okay. Can everybody see that?
Yes.
Yep. Okay, hi everyone. My name is Aaron Miller and I'm a PhD student at Queen's. Vu did a great job there talking us through aerial LiDAR data capture and how he's taken basement information or subsurface information from that. What I'm going to do now is talk about street level data, LiDAR capture and how and why we're going about this approach in Belfast. So, just to introduce you to the equipment we're using, this is the GeoSlam ZEB Horizon. It's a LiDAR scanner, and from the image here you can see that it's handheld. It's got a compact design and it's about 2 kilos in weight, so anybody can really hold on to this thing and not have to muscle it around. Because it's so small, you're able to use it indoors and outdoors. You can do a seamless scan and make your way from the street level into a building and back out and include it all in one model. It's got, we chose this one in particular. There's multiple models, but this one was chosen because of its range. It's got a 100-meter range. So for example, if I was standing, very specific to New York, this example, but if I was standing at the base of the Statue of Liberty, I'd be able to collect data points from the very tip of it from the ground. And the same from the left and the right of the scanner. It collects 300,000 points per second, which isn't going to mean much to you now, but it just means it has a high point density, and this will be shown in the images later in the presentation. Its accuracy is pretty good at 1 to 3 centimeters relative, so each point beside each other will be within 1 to 3 centimeters of exactly where it is in real life. It has up to 30 minutes scanning time, but this isn't a total battery life, this is per scan, so you can do 30-minute scan and put it down and start the next scan, and I'm not sure how many hours you can go for, but I've gone for at least 4 in the past. And one of the big things with this scanner is its price point. Compared to other, compared to aerial, it is just massively efficient. It's $37,000 to buy this device, whereas an aerial survey might cost $500,000. And this can be used over and over to scan a large area, and it's just dependent on how far you want to walk, really. And another thing, it doesn't just have to be held in hand, it can be mounted in mobile platforms. I'm going to show you an example of this later and some plans we have for the future. Okay, so first of all, this is a comparison between some GeoSlam data on the left here and the aerial data, which is currently available in Belfast, which was collected in 2006. And straight away, you're going to think, are these two the same place? Because the quality is just completely different. On the left, you can make out details. This is Belfast City Hall. You can see the columns and see some statue details. And on the right, it looks nothing like it really. You get a brief look at the shape of things. As I said before, the GeoSlam captures 300,000 points per second, and that leads to the point density of this one on the left being 30,000 points per square meter, which is just far above what's available with aerial LiDAR, and what's available in Belfast is 4 points per square meter. So you can really see the difference there. And so how does the equipment work? Well, the equipment works using SLAM technology, as is in its name, GeoSlam. SLAM stands for simultaneous localization and mapping, and it allows the scanner to create a 3D model of the environment around it and locate itself within that environment. This is the same as how robots work when they're moving their way through a room. They know where they are, they're able to know their distance between them and all the objects around them. So how does SLAM work? It uses a combination of LiDAR measurements. As we mentioned, LiDAR is pulses of light, and the machine takes in how long that light takes to return to the machine, and by that gets distances to objects. So we've taken into account distances to objects. It knows where it is in relation to those objects around it. It also uses an inertial measurement unit. Inertial measurement units are typically seen in aircraft, or in this case, this massive one here is from a spacecraft, a NASA spacecraft. So the one in the machine isn't quite as big as this, but pretty much it is used so that the device knows its orientation in space. So it knows if it's what direction it's pointed, it knows if it's been tilted or if it's pointed at the ground or upwards. And using a combination of its distance to other objects and how it's orientated in space, it's able to work out where it is in the map. So a sample here. I've compared some GeoSlam data and terrestrial laser scanning data. That's the TLS, and that's in full color in these images. So the TLS is a server-grade instrument. It's from Faro. It's millimeter accuracy, and it'd be typically used for street-level data capture. Now you can see from these images that the accuracy is, or the size of these images are very similar. This is the same streetscape in Elmwood Avenue in Belfast. The top was captured using the GeoSlam, and the bottom the terrestrial laser scanner. And you're probably wondering, well, if these are so similar in accuracy and I can get a little bit more accuracy out of the terrestrial laser scanner, why wouldn't I just use it? That's because the terrestrial laser scanner here, to measure this streetscape, took about 50 minutes of scanning time. It took 5 8-minute scans to do this street. And then moving the scanner in between, because it's on a tripod, it doesn't move. You do pretty much just set it up, let it do its thing, and then move it to the next spot. I compare this to the GeoSlam. This scan is the exact same area, and it would have taken 10 minutes. It's really just dependent on how fast you can walk. Obviously, you need to have limits on that, but it's dependent on your movement through the area, and not so much setup and having to wait. So this would have been a walk up and down the street, and would have collected the same data. And one thing to keep in mind here is that the terrestrial laser scanner is in full color. It's true to life colors, whereas the GeoSlam it's showing its intensity values. It's because the true color, you can capture it with the GeoSlam, but it's just not as high quality and unnecessary for this project. So we stick with the intensity values. As I said before, although I said it's dependent on how fast you walk, there's other ways to transport the GeoSlam around. And you can see on the right here, my colleague John Manili made a bike mount, and the GeoSlam was actually visible on the back of the bike. And he cycled this through Belfast city centre and was able to collect great data, very accurate. We also had another idea to mount the GeoSlam on a street cleaner. And as the street cleaner drives around the city, it would automatically collect data. And this could be a great way in the future of automating your data collection without having to make specific plans on it. And you could just go out each day and update depending on how the landscape is changing. So what's the motivation for collecting this GeoSlam data in the first place? Well, like many other of the main cities around the world, Belfast is Belfast, New York, and Dublin are all coastal cities, so coastal flooding is a real threat. These maps show our study area in Belfast city centre. The one on the left shows the coastal floodplain present day, and it covers about 60% of the city centre here. On the right, we can see a floodplain climate change scenario for 2080, and you can see that it then covers around 90% of the study area. So coastal flooding really presents a big threat to Belfast and to the other two cities as part of this project. But what's not included in these flood simulations or scenarios is the underground spaces within the study area. These underground spaces we think will create a massive change in flood models. They act as sinks for floodwaters, should impact flood dynamics at the street level. So it will make a big difference to how the water flows through the city. And by including basements and underground structures in these flood plans, we'll get a better idea of the risk to the occupants and the contents of those basements. As you can see before, the flood models are based on data which isn't as dense as what we're capturing with the GeoSLAM. So the more accurate data we're collecting with the GeoSLAM will lead to more accurate flood models. This can improve emergency planning and will raise public awareness, letting them know the danger of flooding. So as I said, the data collection goals. Here's a better look at our study area in Belfast. You can see it's right on the east coast of Northern Ireland. If you didn't know where Belfast was, you can see our study area is in the middle of is in the urban centre, and it's right at the coastline. What we want to do is create an accurate 3D model of our 1 kilometre squared study area. As I said, map and identify the underground spaces and generate more accurate flood models. So there's not much basement information available in Belfast. This map on the left shows what we do have, and this is a database provided to us by Belfast City Council. Now what they've done is they've got all the planning information from the mid-70s up until about 2018 and attributed planning information to land parcels within the city centre. What you're seeing in the map are those individual land parcels. Now the yellow parcels highlighted are ones that I've extracted, which have an attribute related to either underground spaces or basements. So this is all of the information we have with regards to basements within our study area. The problem with that is these are land parcels. Each one is not relevant to a building, and they're not the same shape as the building, so you're not getting the dimensions of the basements or the depths. We're also not getting the entries to the basement. We don't know if there's vehicle entries or if it's just windows or doorways. We don't have any of that information, so we don't know how these would interact with floodwaters. And we also don't know, well, they do have a use with them, but a lot of them, from my experience, have been outdated. And we know that uses of spaces change over time. So we want to update all of this information. So now I'm going to show you a quick video of how simple it is to use the GeoSLAM. The GeoSLAM only has one button on it. It's really just, it's a button to start recording and end the recording. The only thing you have to keep in mind is that you have to start and end in the same place. And you'll see during this video, which John Neely and my colleagues put together once again, it's very simple to use. It simply works by walking around the object or structure or block that you want to map and stopping. And then from that, it's very easy to generate a 3D model from it. Now, it's pretty easy. The scanning process itself isn't very difficult, but I just want to touch on geo-referencing the data before I get on to more of a large-scale data acquisition method. So geo-referencing is when, as you can see from the end of that video, there's a model created, but that model is not related to anywhere on the globe. It's just floating in space and on your computer, practically. So what we have to do then is geo-reference it so that when we input this into a mapping system, it's in the correct place. And this allows us also to stick multiple scans together and make a larger city model. So how do we do this? There's two ways I've been using to do this. and we use recognizable points on the ground for both ways. And the first method is to use a reference plate, which I'm going to show on the next slide. And the second method is to use identifiable features on the ground and find them within the scans afterward, which is less accurate and kind of a backup way of doing it. So you can see me there on the left in Belfast. There's the Titanic Museum and the Harlem Wolf cranes, and I'm collecting GPS data. So the first method here is the reference plate method. So again, on the left, you see the GeoSlam. At the bottom, this is an attachment called the reference plate. It's quite heavy, actually, probably 500 grams or a pound, and there's a hole in the front of it. So all I do, as I'm walking around scanning, at any point, I can find a feature on the ground as shown here on the right, either a recognizable feature. So here you see the end of a brickwork, and it's quite easy to find the point, or lines and road features, which is what I use mostly. And all I have to do is put the hole in the reference plate on one of these points for 5 seconds. And when I revisit the scan afterwards, these points are highlighted, and I'm able to switch out that point information with GPS data I capture afterwards. And therefore, the scan is georeferenced. And the second way is not as accurate as I said before, and it's a little bit more tricky. So scan has been collected. I go into the scan, find road markings. As seen here, you can see the letters. This would be a prime area to do it. Or street coverings here, not as clear, but these can be used. I then make a note of which ones I want to collect, go back into the urban environment and collect these points with the GPS. Afterwards, I can then input both in the software, and I simply match up the scan with its features to the GPS points I've collected, and it lines up, and then that is it georeferenced. So how do we go about actually collecting GeoSlam data on a large scale? Well, this is a part of a map of the Belfast city centre here. And each of these colours represents an individual scan I have collected. So these are not only city blocks, as you can see, separated by roadways, but they're also individual scanning blocks. It's pretty much what I do for multiple reasons. Is I stay to the pavements, I circle the area that I want to scan, just a loop. So it has to be in a loop because of the SLAM technology means that the GeoSlam has to start and end in the same spot. So wherever you start scanning has to be your end point also. So this has to be taken into account when planning. So the main thing I want to do is get the outside of each block. I do this so that I don't have to cross roads, because realistically I don't want to be crossing through traffic while I'm concentrating on scanning. Although the GeoSlam is able to capture data from both sides of the street because of its range, I want to focus on my side of the street, so I walk on each pavement. I go in and out through the back alleyways, but although they're not as important, I have a main focus on the outside of each block. And this is also an easy way to organize this, because if you have a full finished scan for each block, you can go back and get those later, and you know, like, this is complete, this is everything in this area. Like, I've got all these coded, so I know exactly where they are. It's easy to keep track of and stick them all together afterwards. If we look at this, this is the orange scan here of Belfast City Hall, as you can see at the left, and this is the output created from walking around it. So if you can see here, the tree line, the pathway, the pavement is actually just outside that tree line, so it gives you an idea of where I walked. I walked all the way around the back here, and this took about 12 minutes to get all of this data. And this is one scan. It's about 150 to 100 by 195 meters. There's 54 million points there, and it took 12 minutes, as I said. Now you'll notice the difference between this and the aerial data that VU showed is that this does not include rooftops, and you can see some blank areas here. And this is as a result of Lidar working as line of sight. So from the street level, if I'm not able to see the roof, then either is the scanner, and it's not going to include that information within the scan. But as this is not our focus in this investigation, it's not a massive problem, and this can easily be added to already existing aerial models, which do include rooftop information. So if we want to make a bigger model than just that one I've showed very quickly, we're able to do that in the software which comes with the GeoSlam. It allows you to line up to four to five scans very quickly by roughly lining them up, and then it it uses similar features from each scan, geometric features to line them up very quickly and accurately, actually. But it has a limit of four to 5 scans, so that's why georeferencing has to come in. So what we can do here is, top again is the orange, the City Hall scan. It's been merged with 2 blocks close to it, the red and yellow, so 3 scans here. And this means one model has been output, and this model is 260 meters by 195 meters, which is much bigger. And by doing this, we massively reduce the amount of time we have to spend collecting GPS data points by a quarter of the points we would need originally. And collecting GPS points is one of the massive tasks to go with this. It takes the most time. The GeoSLAM itself is easy, so by limiting the amount of time we spend doing that, we're really speeding up the process. Results. What do we get from scanning at street level? Well, here one of the more historical buildings or older buildings around City Hall, and we can see that this is a Google Street View image, and you can see slightly that there's windows below street level. But with the GeoSLAM, you can see that the staircase down to the basement level has been captured fully. We can see the individual steps here. We can see people sitting at the bottom, and we can see window details and lots of facade details. Here's another result on a more modern building. Again, on the left, we can see the Google Street View image, and on the right, we're seeing how, without me entering this underground car park, it has been captured from street level. So we can see the whole ramp down to the underground car park structure below this office block. We can see its depth, and that's only, you can actually see the entranceway here, and it's only halfway open. And it was just me walking past. I didn't really stop there or anything. Here's another example which is quite interesting. This is an apartment block in Belfast, and it has this unique feature where there's an underground car park here, but there's ventilation and lighting being let in by these openings here, which is just pretty much like grates, I'd say, on the wall. And from those alone, just from me walking past these, I'm able to get full depth measurements using the GeoSLAM, because the laser is able to penetrate through that area, collect depth measurements, and bring them back to the scanner. It's really interesting here, because walking past, you would hardly even notice that, but you can see it clearly on the right. Another benefit of the GeoSLAM is being able to actually enter these underground spaces. Now, compared to the aerial data, which collects data straight down from the air, obviously, we're able to enter these spaces, and this is an example of us walking through a pedestrian underpass, which is a tunnel which allows passage safely from one side of the street to the other underneath the road, so you don't have to deal with any traffic. This is possible with a terrestrial mounted laser scanner on a tripod, but as you can imagine, it would be multiple scans in here. It would take a long time, but with the GeoSLAM, you're able just to walk through it, walk back, and continue your scan. And we've got very accurate measurements of it here. We're able to calculate the volume and know the whole shape and how water might flow through it. And on the bottom right here, you can see a 3D model that's been created, and that's to estimate the volume of this area, and you can see the full layout of how that tunnel is shaped. Our final example here is the Belfast Entries, and these are historical narrow alleyways in Belfast. Now, on the bottom right, you're seeing the 2006 airborne Lidar data for Belfast, and you can see there's not much detail here. It just looks like, well, it's hard to tell at all. It just looks like building tops. But on the left, we can see the GeoSLAM data in comparison, which you can see the crisp details, and you can see the obvious alleyways in between these buildings. Now, these are important details because they're not captured at all in the airborne data. But with GeoSLAM, we're able to capture the details, the elevations, their width, the volume, and this would have a massive impact on flood dynamics in this area, as water could just pass through these easily and would affect all the buildings in between. So in conclusion, the GeoSLAM is a cost-effective way of mapping the urban environment. It's relatively accurate, as you can see, with its comparison to the terrestrial laser scanner earlier. It's highly maneuverable, which is one of the massive positives it has, where we can enter the underground spaces. We can get into tight spaces where other things can't, like aerial data misses out on these narrow alleyways and underground spaces. And the terrestrial laser scanner is very slow to move around compared to the GeoSLAM, which is very fast. Not as fast as aerial, but you have to weigh these things up. And it allows for street level data capture, which is which allows for more accurate data to be collected from building facades as opposed to aerial data, which is, mostly concentrates on the ground level and on rooftops. That's everything from me. So if you have any questions, please let me know.
Thank you.
Carrie, are you guys able to see my screen?
Is that risk communication?
Yeah.
Yep.
So just, what do you do with something like this? So the idea is here's that building, and then, you have the opportunity to do some modeling, both as these spaces as sinks and as areas of particular risk, as well as using this just to communicate to residents and building occupants about, what might be going on locally in their neighborhood. So thank you very much.
So who's up next?
I think we've both used up the time.
Okay.
But we're available for questions for whoever would like to stay. At least most of us are. So
we have, I think I scheduled this on Teams, which has been nothing but a nightmare this morning for me. 15 more minutes for questions. So I have some questions. How far down? So we get the sidewalk, which is what this was initially about, but what about the street itself? How far down can it go?
Sorry, Terry, I'm not sure I understand the question.
Well, okay, hold on. Let me turn this thing off because I'm hearing myself in stereo. It's just the phone started going, everything. So you're walking around on the sidewalk or the street, and you're looking at the buildings and what's below the sidewalk. What is the capacity to look at what's below the street itself, for utility infrastructure?
I mean, with this, it's all line of sight. So if the DOT has, ripped up the street and there's a major capital construction project going on, obviously anything that's in there could be documented. It's not going to see through anything that's solid.
Okay.
But as Aaron showed, that he can stand in the public right-of-way and still get a pretty good idea of what some of these volumes are underground of these, garages and things that otherwise would be hard to detect, as well as the work that Vu did, where you're seeing stuff in the backyards.
Okay, so this is definitely just for sidewalks at this point, which is not nothing, by the way. And the other question I had is, so you're thinking of putting it on a street cleaner, right? So to do this, the street cleaner they'd have to observe the protocols of starting in one place and then ending in the same place.
Yes.
Okay. So that's the, because I was getting all excited about sanitation trucks too, but they have routes, and I don't know that they come back to the same point. They go all over the place. Those were kind of my questions. Does anyone else have questions from the working group?
So I raised my hand. Do I get to have a question?
Yes, you do.
Okay, hi. So I'm a person who's very much into underground and trying to take Lidar underground and at this level of accuracy is something that's of great interest. And I think the registration in a GPS denied environment becomes a challenge. But what also becomes a challenge is actually combining different data streams. So the idea of working with, say, radar, ground penetrating or otherwise, or some other geophysical techniques, developing a really more complicated suite of spatially registered measurements that could actually be combined to great strength. Who's working on that kind of an application? Do you know?
Yeah, so Michaela's group is leading that, but right now we're using above ground. So she has the LiDAR data. We have a co-registered 2D imagery data, but we also have hyperspectral data for that. And then to be able to not only just, co-register this and see this and overcome that 2D versus 3D, but, to do this then in high performance computing, in some type of distributed or parallel computing, because that's where we've got to go, as painful as it will be for people like you and me, Priscilla, but that's where we need to be. So
yeah, and so I think the applications on this, there's a lot of interest. The mining industry is the one I'm thinking of, although certainly for urban civil purposes it's applicable as well. But the combination of all these different platforms, drones and land-based and satellite-based imagery, and to really get a good, a lot of these processes, like some of you might know about mining and tailings dams that have been failing and that are the subjects of huge interest right now in the industry. And the sense of actually having spatial and temporal registration on a variety of measurements is huge, and it needs a really good demonstration that EU puts out money more than the United States does to support something like that. But I figured maybe there's something in the EU that's actually focusing on that kind of integration of measurements.
Michaela, you want to make any comments?
Sorry. No, I think, yes, absolutely. There is need for such an application. And what we're doing in this project, we're trying to integrate different type of data, particularly LiDAR, different collection techniques, so aerial versus terrestrial and mobile LiDAR, as well as imagery of different type. But there isn't really on the market an application that does that yet.
No,
so
not yet. Yeah, but it would be, I get the feeling that there's little experiments being done all over the place, and trying to find them and pull it together would be something interesting. So, I mean, Deborah, if you were interested in that kind of an international assessment might be something that NSF would be interested from the standpoint of an invited workshop to see what the status is.
It seems like also a good topic for a convergence grant. If there ever comes up one in an area where we can fit ourselves in. So
yeah, right.
I know in the UK, the Research Council are supporting a number of studies that, when you mention tailings dams and embankments, that do time-lapse continuous monitoring of failing embankment structures that are fed with real-life, real-time data into online platforms where you can monitor the processes that are going on, together with surface data on subsidence monitoring and things like that at the same time. And on the other hand, in other urban environments, people are developing geological models for the subsurface that take into account borehole data and to a certain extent geophysical data, but the connection to the above ground is not quite there yet, where you can have a seamless model of scanning from the above ground down into the underground and combining different data sets.
Well, I think, yeah, you're right. And it's got a visualization problem as well when you start putting that together. And I think that the interesting thing about tailings dams, though, is that they build it over 50 years, right? So you actually have a construction history that lasts that long. The stresses, some of these tailings dams are now the highest water retention dam that we have built is on the order of 300 feet high, 100 meters high. We have tailings dams that are over 300 meters high, and some being planned for up towards 1,000 meters high. And this is just a unique opportunity to actually make time series measurements that validate the function and performance of dams. And it can go similarly back to the underground construction environment where you're doing something over time and the ground is gradually responding. So, I mean, there's getting that time in there along with the spatial resolution is opening up many different possibilities for doing better engineering with earth materials.
And I think as American cities start to explore and actually start implementing geothermal, it will be important to have those kind of tools, because we know from countries like Germany that sometimes these installations can have massive effects over large spatial areas.
Right. Yeah. Lots of applications. Good. Well, thank you so much.
Any other questions?
Yeah, hey Terry, it's Tom.
Hi, Tom.
I'm just curious, has anybody ever challenged this on privacy concerns, especially as the technology advances to a point where you could do subterranean analysis of private property?
So far, both in a EU and a US context, the universities have basically, and the funding agencies too, if you can't see somebody's face, and at least from the air, if you can't collect a license plate, they consider that as exempt from security issues. I mean, we send satellites over all the time, catch people, sunbathing in their backyard. So it's not a new problem. Obviously, what the technology Aaron's showing us today is, potentially more problematic in terms of being able to collect license plates, or even somebody on the street. So.
Well, I think the other thing that we've seen with the use of the GeoSLAM was that when you're walking past a building with a glass facade or with large windows, you actually be able to measure inside the building as well through those openings. You see the footprint of the room inside in your scan. So it depends on the level of detail that you want to go to. In our project, we're only interested on the outside facade and indicators that show us there's basements, but in theory, there is maybe an area that needs to be looked at in terms of privacy concerns.
We just got a ruling from NYU on collecting basically Wi-Fi signals or Bluetooth signals off of smart devices. If you walk down the center of a street and you're able to pick up those devices from the center of the street to maybe make an assessment of whether those subterranean areas are occupied or whether they're storage. And NYU's position legally was that if you're in the middle of the street and you can sense it, they have no issue with it.
I'm sorry.
Terry, are you trying to speak?
I didn't hear the end of that, Deborah.
Oh, the feeling is that if you're standing in the middle of the street and you can detect something that's being actively emitted from somebody's home, the NYU's position is that they've kind of lost their sense of privacy by emitting this signal.
Oh, okay.
I don't think something like this has been tested in court yet.
Okay, well, it's a thing.
Well,
Definitely a thing.
We've had this urban observatory on the top of what was One Metro Tech and now over at 370J, where we collected, not we, but the urban observatory collected light from people's homes to see, are people sleeping? Are they not awake? So it's all these kind of gradations, and obviously as equipment gets better and the software gets better as well, it is an increasing concern.
Okay. All right. Well, we're a million years away from us doing any of this, but
Well, and that's not true. I mean, you guys, the city did the cyclomedia data. You know, they put a van on the street, or hired a company to, and they, you know, went down the street and collected data that's not so dissimilar from this.
What agency? When was this?
I think it was under Do It. Vu, was that 2017? Do you remember when you were here?
I don't remember the exact year.
I think it's around the time of the last released Lidar scan, so around 2017, 2018.
Yeah.
And is it possible to mask? You know, you collect it. I took the IRB training course a couple of weeks ago, and there's this policy where if you've collected really private, personalized data, that you can take it out, you know, in the final output. Like, there are ways to protect privacy once you've collected it, right? By taking it out.
I mean, Google Street View, my understanding is that Bloomberg, you know, our past mayor, that his ex-wife's residence is actually blurred as you look. If you go down to Google Street View where she lives, you cannot actually see the building.
So, I mean, I'm just thinking, if we get to the point of this, that there are methodologies and protocols to sort of strip out the personally identifiable data, because honestly, we don't want that. Well, we in the Utilidor group don't want that. I'm sure there are others who might want it, but you know, there should be ways to sort of strip it out. So, any other questions? We're getting close to the 11:15, so this has been great. Thank you very much. The recording is still on, so Deborah, let's get back together, you know, by email, and then we'll talk. What I'd like everyone to do is, what's the word? Get off. And then I'll stop the recording, and I will see about how we send it to everybody. That's another tech thing. But I really want to thank you all for the presentation. This has been very interesting. And we'll be back. And I know the NSF project is ongoing, and that's in Sunset Park and Midtown Manhattan.
No, Sunset Park is the only site we have in New York.
Oh, okay.
And we have Belfast and we have Dublin on this project. So
no, I mean the other.
The other project, yeah.
Okay, so there's more to come. So thank you. Have a great weekend. What's the word I'm looking for? Get off, and I'll do all the administrative stuff. And thank you.
Thank you, Terry.
Thank you very much.
Oh,
Terry, maybe you and I can hop on via Skype.
I don't know. How about give me 15 minutes to get this thing done.
Take care.
Okay. Bye, everyone.
Bye-bye.